Welcome to AQA's AS Physics Unit 2 June 2013 question 5. I actually got that right. Did do a video where I messed it up, so they didn't say that, but just for the benefit of you, just have a laugh at me if you want. Very hurtful. Of course, anyway, so this is the diagram that we get given in the exam. Okay, what it is essentially a glass block made up of three types of glass A, B and C, obviously. Very imaginative, they've called that. Anyway, so we've got basically this red line here is the light ray coming in, and obviously we're going to have to continue that on at some stage. But the angle of incidence from air, which is obviously what's outside it, is 71 degrees, and then we've got this other angle theta, which is the angle of refraction from that. Okay, and it bounces off glass B and then bounces off glass C again, but obviously we'd need to continue that, but we're not being asked to yet, so because we can't be bothered, we're not going to. Okay, so 5A says state the two conditions necessary for a light ray to undergo total internal reflection at the boundary between two substances. Okay, transparent substances. Now really these are it's just a knowledge question. Okay, so the first one, the angle of incidence has to be larger than the angle of refraction, otherwise it doesn't undergo total internal reflection. And another one could be the substance that it is surrounded by has to have a lower refractive index than the substance the light ray is currently in, because if it wasn't and the substance had a high refractive index on the outside, it would slow it down even more than it has been. It wouldn't make sense, and it would just basically, it wouldn't go through the substance. And the angle of incidence needs to be greater greater than the critical angle. Okay, which is something we're going to go on to explain in this question. But really, you could just have a look online for that. Okay. So, really that first one, that incidence must be bigger than refraction. That's always going to be the case, okay? Right. So that's 5A. So there are two conditions there. Okay, now this next part, we're not asked to be in. It's a very rare question they might ask. But basically, we're told the refractive index of A is of glass A is 1.8. So the refractive index, I'm going to call this N subscript A, okay, is 1.8. And we're asked to find the speed of light in that substance. Okay, now you should know that the speed of light, we'll call this C. Okay, so this is part B, is 3.0 times 10 to the 8 meters per second. Okay, as I said, you should know that obviously, but I think it's in your formula sheet anyway. But it's good bit of knowledge to be able to remember these things. Okay, so what we mean by the refractive index is the amount, the ratio of which the speed of light is slowed down. Okay, it's obviously not sped up. Okay, so if it's slowed down, then we have to, by this ratio, we have to divide the speed of light by the ratio of the refractive index, because when we divide it by the refractive index, we're working out the ratio as being slowed down. Okay. So therefore, we just come up with this formula, which is CA, which is the speed of light in substance A, over the speed of light, which is 3 times 10 to the 8, or C, meters per second, obviously, over the refractive index of substance A, or 1.80. Sub that in your calculator, should get a value for CA, which is equal to, so I should have had this straight away, but obviously that's slick. Okay. Why has it gone backwards? I do apologise. Yeah, this isn't going to smooth. Okay, so question 5. Which is 1.7 times 10 to the 8 meters per second. So it's still very fast, but it's not so fast, obviously, as in air. Okay, so that's refractive index. That's the speed of light in the substance A. Okay, so that's part B. Part C says, show that the angle theta is about 30 degrees. So we're asked to show that this refractive, that's this angle here of refraction is about 30 degrees. Okay, so obviously it won't be exactly 30 degrees, but if you want to use it, obviously we're going to have to use this answer later on, or we might do. Okay, so we use our standard rule, our Snell's law of n1 times sine I is equal to n2 times sine r. Okay, now just subbing what we know. Now n1 is obviously refractive index of substance 1, which is air, which is just 1, times the sine of the incident angle, which is 72 degrees, if you can't really see what I've written, is equal to the refractive index of substance 2, which is glass A, which we know, we've just been told is 1.80, okay, and that's times the sine of the refractive angle, which we don't currently know. Okay, so you could do this in 2 steps, so I'm just going to do it in 1, purely because I'm lazy. Okay, so what you would do is divide both sides by 1.8 and the inverse sine. Okay, so therefore R would be the inverse sine of, okay, sine of 72, or 1 times sine of 72 over 1.80. Okay, get a value for R, which should be, it's set, you want it about 30 degrees, but the actual answer you get is something very smooth. It's actually about 30. It's 31.9 degrees. Now that is about 30 degrees. Okay, so don't be put off even though it looks like it can't possibly be right because it's a bit too high. But as I said, it's about 30 degrees. You don't ask you specifically to show that it is 30 degrees. It's about. So don't be too put off by the fact it's not exactly 30 degrees. Okay, many of these won't be. The refractive index of glass C is about 1.4. Okay, so that's this here. Calculate the critical angle between glass A and glass C. Okay, so the sine of the critical angle. So the sine of the critical, the incidence of the critical, okay, is equal to the refractive index of substance 2 over the refractive index of substance 1. Now, I've explained that in my AS Physics playlist of laws of refraction, one of the videos in there. Okay, so please do check that out if you don't get why we've just assumed that. And if I've not put it on there, I will add another video explaining it. But for the time being, just assuming you can accept that rule. Okay, so it's just a case of now subbing in what we know. So the sine of the critical, which is what we want to find out, is the refractive index of substance 2 over the refractive index of substance 1. Okay, so there's a certain way, so we need to decide which is substance 1 and which is substance 2. Okay, let me just make sure I've got this right. Okay, so the refractive index of substance 2, because it's asking between, we know that, sorry, one sec. We told the refractive index of substance C, which is this glass C, is equal to 1.4, and we know the glass of substance A is 1.8. Now it's starting at A and it's almost entering the glass C. Okay, so therefore substance 2 is obviously glass C, substance 1 is obviously glass A. So it's 1.4 because that's substance 2 over 1.8. Okay, and then you just sine inverse that. So therefore the critical angle, so instance critical, is equal to the sine inverse of 1.4 over 1.8. Okay, so therefore that gets you an angle of critical of 51.1 degrees. Okay, so that's the answer to 5D. Okay, so our next question says, state and explain what happens to the light ray when it reaches the boundary between glass A and glass C. Okay, well, total internal reflection occurs because the angle of incidence is less than the critical angle, which causes it to rebound off the boundary. So remember, this is the boundary between A and C, so what happens at this boundary? Well, it's obviously going to reflect because this angle here is now worked out to be 31.9, so obviously the angle is going to continue to get smaller and smaller. Okay, so obviously it's not suddenly going to jump from 39 to greater than 51.1 degrees. It's very unlikely. So therefore we just assume that it's less, the instant angle is going to be less than 51.1. So if you were to work it out, it would come out to be less than 51.1. And when we say that the angle is less than the instant angle, it will bounce off the boundary and reflect back. Okay, so that's all you need to say, really, for that. So that's I'll plug that up. So, I do apologise, I made a kind of a bit of an error drawing this. I missed off the 22 degrees there, so if you do go online you will see that I've obviously missed off this 22 degrees here. And using alternate angles, because this theta is 31.9 degrees, if you work it out now, obviously you're just going to assume that you're capable of doing that. This angle here, which I'm going to draw in green, is the 22 degrees plus the 31.9, which gets you your 53.9 degrees, which is bigger than the critical angle that we worked out. And if the angle is greater than the critical angle, it will pass through the boundary, because this glassy has a lower refractive index, so it definitely will pass through the boundary. And so that's why that's the answer for part 5e part 1. And then 5e part 2, well, it's just a standard thing of just, something like that. Okay, so I'm kind of carrying it on in green there. But really, it's just a nice little bit there. As I said, the rest of it is correct. I don't know why I made it a little bit of a mess there. Obviously, just missed off this 22 degrees, and I was kind of going, what the heck in my brain am I doing? But hopefully you get the idea. Really, it's quite a difficult one, the last little bit anyway, to spot that. But you should have been able to follow the rest of the question quite well. Now, as I said, I'm more than willing to redo that. I've specified in various questions where I've mucked it up a little bit. But as I said, hopefully you get that, and we can move on to the next question now, which is question 6. And that question is all about progressive waves and phase differences. Okay, and then we're going to polarised waves and stuff. But that's for the next question. So that's question 6. Thanks for watching, and we'll see you in the next question.